Hello everyone, welcome to the section 4.1 notes where we are talking about exponential functions. This should be a pretty easy section because it's going to involve a lot of calculator usage and simply plugging in values into a calculator, but there can be some considerations about order of operations and using parentheses and stuff like that, so we'll jump into it. It's really going to pick up in section 4 once we start talking about logarithmic functions and equations, and also the exponential equations where we're solving for a variable. In this one here, we're only getting some basics about exponentials, like their graphs and how to do calculations with them. So let's see what's going on with number 1. It says the exponential function f of x equals 574 times the quantity 1.026 to the x power models the population of India in millions after 1974. And so there are a few things to look at here. We're looking at how much x should be whenever we talk about a given year. So in the year 2028, we're comparing against the year 1974. So if we want to know what x should be in this case, we need to tell how many years after 1974 the year 2028 is. So x in this case should be the difference, 2028 minus 1974, which that one turns out to be 54. And so in this case, if we're trying to find India's population in the year 2028, we should plug in 54 for x into this equation, and it's going to go right there in the exponent. There is something to note about this, a way that we can interpret what's going on with this expression. 574, if we don't put in power on this 1.026, we just say 574 times 1.026. This should be regarded, and you can look at this as being a percent increase of the number 574. This is a 2.6%, which that's this piece, the 0.026 after the decimal, the 0.026. If you write that as a percent, that's 2.6%, and we're doing an increase of 2.6%. So if you want to increase a number by a percent, you add the percent to 1. If you want to decrease a number by a percent, you subtract that number from 1. So if the population were actually decreasing by 2.6%, then we would multiply times instead 0.974. And this would decrease a number by 2.6%. And so that's something to look at here. What this is actually accomplishing, this exponential function, is it's increasing year after year. And since we could theoretically plug in partial years, it's really kind of day by day or continuously the population's increasing, but it's when years go by, so on yearly increments, the population's increasing by 2.6%. And let's just do it. We will plug in 574 times, and the parentheses can be very important. Here we want to make some parentheses for 1.026 so that we can raise that to the 54th power. And then we go enter. It's going to be 2,295. I'm just going to round it like that, 2,295. I'll say f of 54 is 2,295. And that's in millions. And so this one, that many million, is actually also 2.295 billion. That's supposed to be the population of India in 2028. In 4 years, we can check and see how close that is, but I think it can be up there. All right, so now a graph of a function. All the exponential functions look the same. And once we introduce logarithms, we could talk about which transformations we do to get from one exponential function to another. But the idea for an exponential function, what makes it different from a polynomial, is that the independent variable is in the exponent, versus you can have a polynomial like g of x right here, which goes x to the 4th power instead of 4 to the x power. This one's a polynomial. The one 4 to the x power is an exponential function. And exponential functions, they grow much faster than polynomials, and they also have a horizontal asymptote. They all have the same horizontal asymptote, which is on 0, because no matter how small of a number, which when I'm saying small, I'm talking about these numbers that are very negative numbers like -10, -100, -1000, no matter how far we go in the negative direction plugging in these x values, 4 to that power will never be 0. And it's necessary here to remember some facts about exponents. I want to start 4 to the -1. You have to know that this is 1/4, or 1 over 4 to the first power. So when you do negative powers, it makes reciprocals. So 4 to the -2, this would be 1 over 4 squared, which is 1 over 16. And see, 1/4 versus 1/16. The 1/16 is much smaller. 4 to the -3 power, that's 1 over 64, which is even smaller. So these numbers are getting smaller and smaller like this. But no matter how big we make this denominator, 1 over a big number like 1 over a million, 1 over a billion, it's never equal to 0. It only gets close to 0. And so we have this asymptotic approach to 0 as we come this way. And then anything to the 0 power is 1, so all exponential functions should go through this point, the point 0, 1, and then 4 to the first power is 4, and so I'll put that point on there. And so we will have this point in the graph, the point 1, 4, which is corresponding to the fact that 4 to the first power is 4, and then I want to also make a point for this one, 4 to the -1. I like to always use -1 for x. That gives us a nice point, the point -1, and then 1/4. And then we will also have points like 2, 16, because 4 squared equals 16. So it's going to shoot off the charts. I can't even put that point on my graph. It's just going to be up there. And if we have a different base, for example, 3/2 to the x, we can go through a similar procedure for graphing these. It's going to be a growing function with exponential growth. Exponential growth looks like this, whereas exponential decay is the name for the function that looks like this. And some physical phenomena look like exponential growth, which that can be things like populations. Well, we just saw we made an exponential model for a population of India. There are some cases where we should have exponential decay, which this can be things like radioactive decay, or it's things about half-life. Half-life also has to do with metabolism, and so it could be something like the concentration of some chemical in your blood. As time goes on, it decays, your body metabolizes it and secretes it and so forth. And so the difference between these, this is whenever the base of the exponential function is greater than 1. That's when we will have exponential growth. And the base, every exponential function we can write as a base to some power. Sometimes we'll have an a in front of this, a times b to the x, because we can have a negative there, for example. It can also be vertically stretched or compressed. And then all the transformations that we've done before, we can still do them to this function, but it's just that this feels like the most natural way to write a general one. We don't usually have transformations like left and right shifts necessarily, or vertical shifts, but they can happen. And so just be aware of that. Whenever the base of the exponential function is something in between 0 and 1, so some fraction like 1/2, that would be occurring in the half-life function, that's when we have exponential decay. Notice though, the base is always something bigger than 0. It only could be in between 0 and 1, we get exponential decay, or it can be something bigger than 1, and we get exponential growth. We should never have a negative base. The base also should never be equal to 0, and the base should never be equal to 1. 1 to the x power, this would be a very boring function because it would just be the same thing as 1. And then 0 to the x power, it would just be 0, except for this one's actually undefined whenever x is equal to 0. So this also would be a weird one. We don't care about these graphs. We want to choose different bases. So here, we'll try one where the base is 3/2. We can plug in -1, so get 3/2 to the -1 power. That's going to give us g of -1, which this will just make the reciprocal, which is 2/3. So it will have the point -1 with 2/3. Let's say it's there. Also the point 0, 1, they always have this point because g of 0, that is 3/2 to the 0 power, which is just 1. Anything to the 0 power is 1, except for 0 itself. That's why I'm saying this one, 0 to the 0 power is undefined. We don't say what that's equal to. And then if we plug in 1, anything to the first power is just itself, so 3/2 to the first power is going to be 3/2, which is here. It still is exponential growth, it's just a slower growth. We get faster growth when the base is bigger. And we will carry on. We can do a transformation like this. The graph of 2 to the x, which that one goes through 0, 1, goes through -1 with 1/2, goes through 1 and 2. And so we would have this function, we treat this as the parent function. And then we will do this kind of transformation. If you add 1 to x, you should recall that doing something to the x is going to be in the horizontal direction or left and right direction. We're adding 1 to x, so this is shifting us left by 1, which means this point actually should come over here by 1, this point over here. It will have the point 0, 2 on it because this point 1, 2 should be shifted to the left by 1 to be there. So I'm going to draw what this graph should look like. It will go through 0, 2, it will go through -1, 1, and then it will go through -2, 1/2. And it would become this function. And so that's quite easy. We also have another kind of transformation. If we subtract 1 from the function itself, like what we see here, 2 to the x minus 1. This -1, if you recall, this is accomplishing a shift down by 1. And we already have the graph of 2 to the x. Let me just scroll up so that we can see that one. It's there. These points should just come down by 1. So it actually should go through the origin, the point 0, 0, and then the point 1, 1. And then this point should be shifted down by 1. Maybe worthwhile to just calculate that one, unless you could figure out what 1/2 minus 1 is. That's what we were doing, but in case you figure out which point that is, 2 to the -1 and then -1. There goes 1/2 minus 1, which is -1/2, so it should go through that point. And it's going to have horizontal asymptote. This time the horizontal asymptote itself shifts down by 1, so it becomes the line y equals -1. Now we're getting into some other exponential problems, which these ones I would regard as being the more normal style. Exponential functions in general, they usually have the base of e. This feels the most natural, and indeed you'll see that the word natural is used in conjunction with this letter e. When we're talking about logs of the base e, it's called the natural log. And so this number e, it's approximately 2.72. And there are many interesting facts about this number, but suffice it to say it's almost 3. And it's an irrational number. This decimal goes on forever. But right now we only want to evaluate this function on a certain x value. So this says that this function models the percentage of high school seniors who applied to more than 3 colleges as years go by after 1980. And we're wondering which percentage of high school seniors applied to more than 3 colleges in the year 2016 according to this model. So that's something we could historically check how accurate the model is. But for the time being, we're looking for a percent. So when we get a number for this, it's read as the percent. And how it goes is it's something like in 1980, there must have been 32.7%. And then it's increasing by around 2% every year. And what we will have is g of which year should, or what should we plug in for x? It's years after 1980, and we're talking about 2016, so that's 36 years after 1980. And so we should go 32.7 times e to the 0.0217 times of 36. And depending on which calculator you're using, we may need more or less parentheses here. But if we, in the case of my calculator, I've got this e button. There's actually 2 different e's. This e would just give us the number e. This e over here, where I go second ln, this gives us e to the x, so it's already going to come equipped with an exponent right here. I want to go 0.0217. I'll just say times 36 like this. I don't need any extra parentheses, and go. It's 71.4%. So it's weird. It's giving us the percents just as a whole number like this, or as the actual percentage, not as a decimal. So 71.4 was the value. 71.4%. And now we have what I would consider to be the most normal application for exponential functions, which has to do with interest. And we've seen some of the other applications like populations. It's really odd to use an exponential model for population because populations do not continue to grow exponentially. There are other factors which contribute to population growth and things that can stunt the growth of population as time goes on. Once people say there become 2 billion Indian people and then there's 10 billion Indian people, they start to compete for space, and something's going to happen to where the population growth should start to slow down after a while, and we use a different model for that. But with interest, we can not worry about any kind of factors that are going to change interest rates or something like this. We're just going to use an exponential model, and it will be very accurate. So for this one, a sum of $10,000 is invested at an annual rate of 1.32%. We're supposed to find the balance in the account after 5 years. And so there is a percent increase per year, but this is actually a nominal rate. This is not the true rate that there's going to be because we are compounding monthly. So we're not going to increase by 1.32% every month. We're trying to accomplish that percent increase after the course of 12 months, which that gives rise to this formula. It may be familiar to you. I think that the continuous compounding formula we're about to use next, that may be more familiar, but I will write it down what this formula goes, and then we can talk about which are the elements from this problem that we should plug in here. So the P is the principal. Principal is the initial amount of, in this case, it's an investment, and that will be the 10,000. And then R, this is the rate, which it's always the percent. So this 1.32%, that's what we should plug in for R, but it will always be as a decimal. So we actually should plug in 0.0132. That will be the R value. N is the number of periods per year. And so that's the 12 months, so that we're taking only 1/12 of this rate of 1.32%. We only want 1/12 of that on each month, so that after 12 months go by, then we did this 1/12 of it 12 times, so that we end up with 1.32% after a year. Number of periods per year. That goes also here. The n is in the exponent because what we're trying to get for the exponent is the total number of compounding periods. That's how many times this percent increase should take place. And so we multiply the number of periods per year times the number of years. It gives us ultimately an exponent that is the number of periods, the total number of periods in this whole scenario. And so we can plug everything in. It's going to go, the compounding or the balance in the account is going to be 10,000 times 1 plus this 0.0132, which is 1.32%, but as a decimal we divide it by 12, and then we go times, it's monthly, so there's 12 periods per year, and there's 5 years. So 12 times 5 makes 60. There's going to end up being 60 periods total. And I'm going to plug that in. 10,000. Here I will use some parentheses to make this 1 plus 0.0132. I want to divide that by 12, so we'll get 1/12 of that rate. This whole quantity going to the 60th power, and it's going to be, after 5 years, that's not paying the bills, is it, to only gain $600 in 5 years, but that's what it is, $10,000, $10,681.88. $1,681.88, that's the balance. And now the very famous formula for compound interest, because compound interest, a lot of times it's happening continuously, and all of those physical applications, what we're talking about, like the growth of the population in India, it's not that people are spontaneously born. Every person is born on January 1st, and the population increases, and it just jumps up like that. It's that people are born over the whole year, and so all the time the population is increasing. And that's the feeling for continuous compounding with interest, is that this investment of 10,000, if it's continuously compounding, that means that at every moment, this amount is increasing by some percentage. And the formula, it goes with, oh, I need to have a there. The p is going to be there, the same principal in the same position that we had before, but this percent increase, it's replaced by the base of e, and then we go e to the rate times time. So p times e to the rt. This is the continuous compounding formula, and so we've got still the same principle, 10,000. We go e, still r should be the rate, but as a decimal, so 0.0132. And then t is the number of years, so we go that times 5. And then let's see what happens if we compound continuously instead of only monthly, if there's a very large difference in these two values. So we will have 10,000 times, here I'm going to go e to the power, with that keystroke, it's going to go 0.0132 times 5, and that is 10,682.27. So it actually didn't change that much. We got one more, well, I guess 50 more cents approximately. 10,000, here we go, 10,682 point, wasn't it 26? I will round to 27. And it's not very much more because monthly is already a decent amount of compounding periods. If it were compared against the annually, where it's only compounded once, we would see a bit more significant of a difference. But here, it also was a small investment to begin with, only 10,000. And so if we're affecting the latter decimal places on the number 10,000, that's way different than if this investment were maybe 10 million, we would have gotten a bigger difference as well. So that does it for Chapter 4, Exponential Functions. We're going to pick up with 4.2 in the next video, and I hope this was helpful to you. Thanks.